Okay, so you should see popping up on your screen a join code. All right, and an attendance code. So if you're on your phone, you're going to text to this number, 315-363-0905. You're going to text the join code, and that way I'll know you're here, and it will also help me to register your clicks. And even those of you in the classroom, go ahead and do the attendance thing. Minimize and keep open. So what that means is you can still log in your attendance while the screen disappears. So just make sure you keep track of that number, 2092, if you haven't gotten it in yet. And then I'm going to start with a question. So this is just the setup for the question, and then you're going to have some multiple choice options. And is that, yes, that's sharing the screen. Okay. A group of subjects were given ice cream right after waking up in the morning, whereas another group of subjects was not given any ice cream. According to the researchers, those subjects who had ice cream upon waking up in the morning performed better throughout the day and were more mentally alert than those who were not given the ice cream. So what we want to decide is what's the independent variable. So remember, the independent variable is the difference between the groups, and it's usually what's established by the scientists. So I'm going to start the question, and we've got 4 choices there. And you're going to click in what you think is the independent variable. All right, and so now I'm going to start the timer so that we can just hurry up and guess something. Remember, this is participation, so just go ahead and put in an answer even if you're not sure. So on a side note, studies in education show that when you have short, very low risk opportunities to test your knowledge, like having in-class questions or like doing homework assignments, that really helps your learning. So your teachers aren't trying to torture you with homework. It really is educationally sound to assign you homework. Generally, missing one homework assignment or doing poorly on one homework assignment isn't going to really impact your grade, but it does really impact your learning. All right, so we got about 15 seconds left. Get those answers in. Okay, so it looks like most people said the answer was C, that the independent variable was the type of breakfast. So when I give you this type of question, always the answer is going to be in there. That's going to be something that was described. So while alertness was in there, that was something that was described. Time waking in the morning wasn't. They didn't say different people woke up at different times or everybody had to wake up at the same time. So you're going to be looking for something that was described in there. So the groups that they separated into were the ones that were described in that first sentence, or let's see, second sentence. Some got ice cream, some didn't. So C is the correct answer. Let's see where it is. Ta-da. Okay. All right, so let's see what people said. Most people put in the alertness and the performance. So the type of breakfast ice cream or no was our independent variable, and we were looking for the dependent variable. So it's going to be something different. And so, yeah, alertness and performance, again, this is something that was described in the article. And that is what depends on whether or not you had the ice cream. So D is the correct answer there. All right. one last question about this. So in reading about this, it said the study was challenged by some, saying that it might be that the cold effect that shocks the brain and makes somebody mentally alert. So how could we test this effect? So before I show you possible answers, anybody have ideas? How could they test whether it was the ice cream or just the fact that they had something cold? What do you think, Katie?
They could give them something cold other than ice cream.
Okay, so she said they could give them something cold other than ice cream. Anything else? What about ice cream might be making them alert other than the cold? Sugar. So what could we do to see if it was the sugar? Yeah, give them a cookie instead of the ice cream and see if the cookie wakes them up in the morning. Okay, so let's see if these are ways, any of these are ways we could test this. All right, so we got answers across the board, but the most popular answer is any of these. And yes, any of these could work. So if you picked one of them, you're at least partially right. If we give one group ice water, that's something cold. If that makes them more alert, then that tells us that the coldness helps. If we give them sugar-free ice cream, we could see whether the sugar is impacting it. We could give the group donuts, so that has sugar in it, but it's not cold. So all of those things could give us a little bit more information about this particular study. And in fact, they followed up the study with ice water, doing the same procedure with people with ice water. And they said that that did in fact make people more alert, but it did not work as well as the ice cream. So that would lead us to the conclusion that, what? It's a mix of both, yeah. Both the coldness and the fact that it's ice cream or something else about the ice cream impact whether or not, or impact how alert you are. All right, so I'm gonna, okay, so we are going to have a quiz next week. For those of you that are in the classroom, your quiz will be on Monday. And for those of you playing at home, your quiz will be on Tuesday. So you'll take your quiz in person. And your quiz is going to cover the content in chapter 1. So you'll have questions like these ones that we just had here, but also some of the stuff that we've talked about in the videos that we've watched. And that would be parallel to what's in the homework assignment. So don't forget that there is a homework assignment. And if you look in chapter 1, your screen looks a little different from mine, but you should see homework 1, or you have assignments tab, I think. And it'll pop up and you can either do the assignments in here, or if you would rather just write down the questions on a piece of paper and respond that way, you can do that. I'm not sure why you would want to, but you can. But the questions are found at the end of chapter 1, except for this first test yourself question. So those are some ways that you can look for the homework assignment. And that is due Friday at midnight. Okay? Questions about the homework assignment? Questions about the quiz? Electronegativity and polarity. So this is one of the driving things that makes food do what it does. Different food molecules make up most of our food. Water, carbohydrates, protein, and fats make up almost all of our foods. And the fact that some of them are polar and some of them are non-polar and some of them are kind of in between really directs what they're going to do when we mix them together. So for this, we're doing polar versus non-polar. And let's see, forward this slide. Okay, so we're going to talk a little bit about how atoms work. So we all are kind of familiar with the idea of an atom being sort of a circle, and inside is the nucleus that has what things inside of it, the nucleus? Neutrons and protons. And which one of those two tell us what the atom is? Protons tell us what the atom is. Okay. On the outside are the electrons. And so me let Jaden in here. On the outside are the electrons, but they're not just willy-nilly everywhere. They kind of have specific places that they are supposed to be. So they're called orbitals, these circles, and we can kind of think of them as like the orbits of the planets. So that first circle there can hold 2 electrons. It's really small, it's really close to the nucleus, and so that's all it is able to hold. All right, to zoom on this one. The second one, and actually before I move on, notice on the periodic table, there are 2 elements in the first row, hydrogen and helium. Okay, and that corresponds to them having the first ring having 2 electrons. The second row can hold 8 electrons, and the next row can also hold 8 electrons. It gets complicated out after that. There's like some partial rows and they fill in a weird way, but the elements we're interested in are really in the first couple of rows, so this is okay for us. So when we're looking at the periodic table, we notice that first row had 2 elements, the second row has 8, the third row has 8, okay? And that corresponds to however many electrons are in there. So let's take a closer look. All right. So if we have a neutral atom, that means that we have equal numbers of protons and electrons, but most atoms can either gain electrons or lose electrons. Right now, let's focus on a neutral atom. So hydrogen, being element 1, has only 1 electron. Okay, and so let's just kind of keep a bookmark in our mind that hydrogen just has 1 electron, and we'll come back around to it in a minute. Helium, element 2, has 2 electrons. And lithium has 3 electrons. So notice lithium has 3 electrons, but how many does it have in its topmost row? The top filled row. Or the outside layer, I guess I should say. The outside layer that has any electrons has how many? Just 1. And lithium is right underneath hydrogen on the periodic table. So that's the connection, is that we're going to see every time an element just has 1 electron on the outside, it's going to be in that same column with hydrogen. Similarly, beryllium has 4 electrons, so that means that outside layer is going to have 2 electrons. 2 are in the first layer, the inside, and 2 are in the outside. And I'll end up going through this again, but the inside electrons are called core electrons, and they don't really do a whole lot. We never lose those. We don't add anything to those. The outside ones are the interesting ones. They're the ones that get shared. They're involved in bonding. They're involved in ions. So we call those valence electrons with the letter V, okay? All right, so if we do sodium, sodium has 11 electrons. It's right underneath lithium. So I'm going to put 2 in that first row. The next row has 8, so 2 and 8 gets me up to 10. And then I've got 1 more electron, and it goes in the next row. So again, that outside or valence layer has just 1 electron. And sodium is right underneath lithium, which has 1 in the outside, and it's right underneath hydrogen, which has 1 in the outside. Now, similarly, magnesium, which is element 12, is going to have 1 more electron. And so it has 2 in the outside, and it sits right underneath beryllium, which had 2 in the outside. So this is the organization of the periodic table, is that even though it goes in the order of the protons from right to left, the columns are formed by how many electrons are in the outside layer. The columns are formed by the valence electrons. All right, so since the atoms in the second and third rows can get to 8 electrons, we have what's called the octet rule. So that says that atoms are most stable when that valence shell is full. And since the second and third row, full means 8 electrons, we call it the octet rule. Now, we never deal with helium because it doesn't really do anything. So hydrogen this is our first example of hydrogen being a problem child. So its octet rule, it only has 2 electrons. It's full when it has 2. But every other element that we're looking at, they're full when we get to 8 electrons. So in order to do this, they can gain electrons. So gaining an electron would give them a negative charge and making them an anion. They can lose electrons. So giving up an electron would make them positively charged, or they can share electrons. So if they don't have very many electrons, just 1 or 2 on the outside, like lithium, like magnesium, then it's just easier to give away those electrons. I only have 1 electron on the outside, let me get rid of it. And so this is why column 1, we noticed the other day, always forms a +1 charge. That +1 charge is because there's only 1 electron on the outside. And we don't touch the core stays where it is. Calcium has 2 on the outside. And so it can give up those 2 electrons, and that's why it always forms a +2 charge. So while we can technically get into some of the in-between things, we could technically form a calcium +1, it's much more stable for calcium to be a +2 because of this octet rule. That gives the outermost layer of electrons is a complete full layer. Now, if I have a lot of electrons, then it's really hard to pull 7 or 8 electrons away from an atom, because then you've got this really high charge. So instead, when we have 6 electrons, 7 electrons, then we just start adding them in. And the left side of our periodic table with very few electrons are our metals. So what is the right side of the periodic table? The nonmetals, exactly. This is why nonmetals form the negative charges. Okay, because it's easier to add the electrons in. Okay, so the positive charges are the cations. And those of you in person can see my sticker here about the cat with the cations. I'm not sure which side it's on. They are positive, P-A-W-S. So that can help you remember, a little memory thing there. All right. We also said nonmetals can make molecules. So our metals don't really do molecules, but the nonmetals, in addition to being able to just gaining electrons, sometimes they get together and share electrons, okay? So the ones we're really most concerned about are carbon, hydrogen, oxygen, nitrogen, and sulfur. And they're all very good at sharing electrons. All right, so some specifics on ions. We've said some of this before, but if you don't have it down, definitely write it down. Metals lose their electrons and become positive, and the word for that is cation. So expect to be asked what a positively charged ion is called on your quiz. Expect to need to know what a cation is. Nonmetals gain electrons, they become negative anions. So again, know what the word anion means on your quiz. Now, we know that opposites attract. You've heard that. It applies to ions as well as personal relationships. So whenever we make ionic compounds, we're going to get together at least one positive thing with at least one negative thing. And when they get together, we have to cancel out those charges. So we have to have the same number of positive charges as we have of negative charges. You're raising your hand? Oh, sorry. Okay. All right, so we can take 1 sodium and 1 chloride, because it's a +1 and a -1, and put them together to form sodium chloride. And this is the chemical formula of salt. Now, one of the things that you'll see on Canvas is that I want you to start learning some of the common formulas that we have for things like salt and water and stuff like that. And so sodium chloride is one that you should know. So by the end of the semester, if I ask you what's the formula for table salt, you should be able to tell me it's NaCl. So as I start pointing those out, those are ones you need to know. And there's also a page on Canvas called Molecules to Know. And so you can start seeing those. All right, so calcium is a 2+ ion. And we also have biphosphate or hydrogen phosphate has a -2. And I need to work on the subscripts on here. But I can put those two together to form calcium hydrogen phosphate. So when you see in the ingredients list for foods, things that have biphosphate and sulfate and things like that, those are generally ions, and they're generally there to provide you with calcium or phosphorus. You need phosphorus for normal functions. Sulfate, the sulfur can be helpful for building amino acids. So things that have those kinds of names in there are minerals that are there to help you nutritionally. Now for a question. All right. We have the element lithium. Is that more likely to form a positive charge or a negative charge? And some of my periodic tables have disappeared in here. If you are playing at home, you might want to pull up a periodic table on your computer. All right, so this one is not written as a multiple choice. So you can write in the word positive or negative, or you can put a plus sign or a negative sign. I think it will get either of those. You have some questions and homework like this. So once we go through the question, I want to talk to you about how I'm going to deal with quote unquote wrong answers. Okay, so let's see what people said. We've got some people saying positive, some people saying cation, some people saying plus sign, some people saying anion, some people saying positive ion. So there's lots of different ways people responded. When I do a question that's a short answer that you have to type it in, I have to guess at all the ways that you might answer it. And it might not have occurred to me that you would put the word ion after that. I might have thought, well, surely they'll just say positive. So sometimes something that is correct, so in this case, the plus sign is correct, didn't get counted as correct. If that happens on your homework, I go through manually for each question. Anything that's answered wrong, I double check to make sure whether or not it's right. Okay, so don't worry if it looks like, oh my gosh, I should have had that right. You know, that should have counted. I will go back and check those things and fix the grading on that. My plan is to make homework due on Friday, so I have the weekend to look through that, and you can check by Monday or Tuesday and say, hey, Dr. Knapp, I looked and it's still counting it wrong. Question? No. Okay. This one, is the following element more likely to form an anion or a cation? So now we have oxygen. Oh, I got to start the question, don't I? Okay. So we've got anion, negative, and a negative sign. So we're all in the right direction there. But when I hit correct, apparently I didn't anticipate people putting in a negative sign. So I'll probably go back, since that's kind of an obvious one, I'll probably go back and add that as an answer. So the next class that does this will be fine. But for you guys, I'll have to manually change your answers to being called correct. All right, one more. Now we're looking at calcium. So we've dealt with this on Monday and Tuesday. That's in the second column. We call that the alkaline earth metals. All right, so we've got mostly positives, one negative, and the correct answer is that it is positive. So notice that we can't see who answered what. So if you're the person who got the wrong answer, that's not to shame you. That's to make a mental note. Oh, I got to check to see why I thought it was negative. Make sure I remember that the path to get to positive. So how do we know that this is going to be positive? Because it's a metal, and metals only form positive ions. And how do we know that it's a metal? It's on the left side of the periodic table. Okay, so left side are positive metals, right side are negative anions. Okay, so now we're going to get to polarity. If I have two atoms of the same element, a lot of times they can share electrons with each other. So hydrogen is in that first row. To fill out its shell, it only needs 2 electrons, and it starts with 1. So if I have 2 atoms of hydrogen, each of them has 1 electron, and if they share them, then that means they each are sharing 2 electrons. So when they share electrons, both atoms get to claim those electrons as their own. And so this is what we call a bond, or a covalent bond. 2 electrons shared between atoms is a covalent bond. Now, when they are the same atom, they share equally. It's like identical twins. They're equal in strength. And theoretically, they play nicely together, but who knows? All atoms have what is called electronegativity. And this is something that refers to how well the atoms will share those electrons with atoms that are not like themselves. So if I look at small non-metal ions, the really teeny tiny ones like fluorine doesn't share very well. Oxygen doesn't share very well. They're greedy. Oops. They're like your little brother or sister who mom says, well, you have to share with them. They're too young. They don't know better. Okay, so the little ones don't share well. And the little ones are going to be fluorine, oxygen, and nitrogen. Now, they get bigger as they go to the left. So it's all on a scale. But fluorine, oxygen, and nitrogen don't share very well. So the electrons are drawn more to those atoms than to other atoms. So that side of the bond is more negative. So we saw with the hydrogen, they were sharing equally. But if I put a hydrogen next to an oxygen, the oxygen is going to pull on those electrons more. It's going to hold on to it more. Okay, so the bond becomes polar, and we call the molecule a dipole. So dipole is a noun that refers to something that has the adjective property being polar. This is what governs the polarity of the whole molecule. So we first look at individual bonds, and then we look at the effect on the whole molecule. Still see a couple of people writing, so I'm going to wait a second. All right, so here's the periodic table, and the numbers that go with the periodic table is the scale of electronegativity. And this is in your book, so you'll have a reference to it within the chapter. The electronegativity of fluorine is the highest we can possibly get, so it's 4.0. Now, there are a couple of different scales. This is what's called the Pauling scale. Don't need to know that. So it's the highest on the Pauling scale. There are other scales where 4 is not the highest. But for our purposes, fluorine is the most electronegative. It is the greediest. It wants the most electrons. Now, it doesn't appear a lot in food, but it's helpful to remember that it is the highest because everything near it is also greedy. So chlorine, which is right below it, and oxygen, which is right next to it, those are also very greedy for electrons. They're going to pull on those electrons a whole lot. And then nitrogen pulls on the electrons, but not as much as oxygen. So nitrogen's a little bit greedy, but not as greedy as oxygen. And by the time we get to carbon, a little bit less greedy. Now, hydrogen is kind of our, again, problem child. It is small. It is our smallest our smallest atom other than helium. So you would expect it to be very, very electronegative. But since there's only one proton in the middle, it doesn't have a lot of pulling power. So rather than following that rule that because it's small, it's very electronegative, it actually sits right around boron and carbon. So it's 2.1 instead of 2.5, but it's very close to carbon. All right, so thinking about that, with fluorine being the most electronegative and things near chlorine being more electronegative than things farther from fluorine, is carbon or oxygen the more electronegative?
I usually pop up here.
Huh. Let me. All right, we won't worry about that one, but if it happens on the next one, let me know. Okay, so a little bit of a split here. Oxygen is closer to fluorine, so oxygen is more electronegative. All right, we're going to try this one again. Is it showing up for you now? Okay, so some people are not getting this to show up. If you look at the screen at the top, you're going to text 1665 and then your response to that same phone number as before. Okay. So most people said chlorine, and again, chlorine is right below fluorine. So since it is right below fluorine, that tells us that it is very, very close to fluorine and very electronegative. Carbon is several elements away, and so it's less electronegative. Okay, so water is probably the most important molecule in your body, most important molecule in food. It's pretty much in everything, and it is made up of oxygen and hydrogen. So as I said, oxygen's really electronegative. It's really greedy for those electrons. So the upper part of this shows one way we can think about sharing those electrons. Oxygen has 6 electrons. I'm sorry, it has 8 electrons, 6 on the outside. So the inside ring of our oxygen shows 2 electrons. And then it has 6 of its own, and then it shares 1 with each of the hydrogens. So now oxygen has 8 on the outside, filling the octet rule, and hydrogen has 2. That's part of its sharing. So that sharing is the bond. So it's bonding, and the whole molecule is neutral. The whole molecule is neither positive nor negative, but the side that has oxygen is negative-ish, weakly negative, and the side that has hydrogen is positive-ish, weakly positive. And so what that means is that when I get water molecules near each other, the oxygen side of one molecule is going to go near the hydrogen side of the other molecules. So the negative side is going to be attracted to the positive sides. So one way that you'll see this sometimes is there's this symbol called delta. It is the lowercase delta in Greek. So you might be familiar with from like sororities and fraternities, the triangle is delta. The lowercase delta kind of looks like somebody made an S and then connected the bottom loop back up again. So we do that delta and a negative to say it's partially negative or weakly negative, and then we use the same symbol with a positive to show partially positive or weakly positive. All right, so water is a very polar molecule. We'll talk later about how it also has a property called hydrogen bonding. We're not going to get into that right now, but it is very polar. Polar molecules can dissolve ions. And so the reason why salt can dissolve in water is that when we have sodium chloride, sodium is the +1, all the negative sides, which are oxygen, point towards the sodium in the middle. All right. Now, there's also chloride in the water. Does chloride form a positive or a negative charge? So it's a nonmetal, it's going to be negative. And since it's negative, is it going to be attracted to the hydrogen or the oxygen? The hydrogen, because the hydrogen has these little delta pluses on it. So our chlorine might be sitting over here, okay? So we often say like dissolves like. Polar things will dissolve polar things. So water is polar, so is what we think of as alcohol. Alcohol is also a chemistry term that refers to a whole big bunch of molecules. But drinking alcohol, the kind that would be in beer or in cough medicine or in food flavorings, all of that is a small molecule that is polar. Sugar is very polar, and acids are very polar. So these things dissolve very well in water. In contrast, we know that oil and water don't mix. Well, that's because oil is nonpolar. Fats are nonpolar. Cholesterol is nonpolar. Wax is nonpolar. If you've ever seen somebody who's waxed their car and puts little droplets of water on it, or it rains and there's little droplets of water and they beat up because the wax and the water are so repulsive to each other, okay? So nonpolar does not mix with water. Polar does mix with water. So this just says the same thing, like dissolves like. Will honey, which is polar, it's got sugar in it, so sugar is polar. Will honey dissolve in water or will it dissolve in oil? Okay, and if it's not popping up for you quite right, up in the corner there it says text 3920 and your response to that same number. And these are going to be similar to questions I might ask on your quiz. So I might ask on your quiz, is honey going to dissolve in water? Honey is polar. Now I do expect you to remember that water is polar. And I do expect you to remember that oil is nonpolar. But I will tell you the thing that I'm asking about, honey or whatever, whether it is polar or not. All right. So most people are saying water. Somebody said honey and water. That is correct. So since honey is polar, it will dissolve in the polar water. Okay, let's try another one. Candle wax. Now, candle wax is nonpolar. Am I going to be able to dissolve that in water, or am I going to be able to dissolve that in oil? Come on. Why are you not going forward? Oh, I think this was the last slide. Okay. All right, so do you feel comfortable with polar versus nonpolar from what we talked about today? Excellent. Okay, so the next thing that we're going to start talking about is our major food molecules. We started talking about carbohydrates, and we started talking about proteins with our activity on Monday and Tuesday. Proteins, carbohydrates, and fats are primarily organic molecules. So what we're going to look at next is what do we mean by organic, and how do we know whether those are going to be polar or not polar? All right, so a lot of times when we think of the word organic, you hear about organic cotton, you hear about organic food. We think that means, oh, it must be natural. It must be healthy. Now, in reality, any apple or any meat comes from a living thing, so it is natural. So generally in food, that means that we didn't prepare or raise or grow that food with man-made chemicals. But there are certain man-made chemicals that are allowed and certain ones that aren't, and all of that. So sometimes we think of that, oh, maybe what we mean by organic is that it's healthy, it's better for us. And sometimes that's true and sometimes it's not. For chemistry, though, we have a different definition. So in this class, when I say organic, I'm not talking about how I grew the food. What I'm talking about is, does the molecule have a lot of carbon in it? So organic just means it's carbon-based. You are all organic because you are all carbon-based life forms. Now, technically, it's a little bit more than that. We need to have either carbon-carbon bonds or carbon-hydrogen bonds. So every organic molecule, except for one, will have multiple carbons in it, and usually a lot of hydrogen as well. Methane is considered organic, even though methane has only one carbon and 4 hydrogens. So that's just kind of a side note. We don't need to memorize that at the moment. But it gets thrown in with the organic molecules. So we have lots of carbon-carbon bonds. And so remember, if I have the same element, then I have non-polarity, that they share pretty equally. Now, carbon and hydrogen are different elements, so that bond is a little bit polar. But what ends up happening is that the hydrogens spread themselves out so much that it all kind of balances out. Now, some organic molecules, not all of them, some of them might also have carbon-oxygen bonds, carbon-nitrogen bonds, or carbon-sulfur bonds, and those are going to create some polarity, okay? So the backbone or the basis of organic molecules is nonpolar, but I can throw in some polar things. Well, some people are not getting the slideshow. Okay, so now those of you at home can also see what we're talking about. Okay, so organic things in chemistry are carbon-based. They have carbon-carbon or carbon-hydrogen bonds. Sometimes they will have the electronegative elements. And again, this slideshow is going to appear on your Top Hat page. So if you didn't get to see this for very long, you'll be able to see it after class. Okay, so are carbon-based things polar? If I only have carbon and hydrogen, their electronegativities are 2.5 and 2.1, very, very close together, and they have a lot of symmetry, so they're mostly nonpolar. Any molecule or part of a molecule that has lots of carbon and hydrogen is going to be what we call nonpolar. If I have any carbon and oxygen, I've got a difference of 1 between 2.5 and 3.5. Remember, our scale only goes to 4, so this is 1 out of 4. That's a very polar bond. If I have carbon and nitrogen, I've got a difference of 0.5. So that's closer to the hydrogen carbon difference, but I tend to have far fewer nitrogens, and because of that, I don't have symmetry to balance things out. So these tend to be polar, just not as polar as the oxygen ones. Huh. I wonder if I can draw in here. Apparently I can. All right, so oxygen and nitrogen are going to be our keys to knowing whether something is polar or non-polar, as far as food-based molecules are concerned. All right, so a lot of organic compounds are called hydrocarbons. Hydrocarbons only have carbon and hydrogen. Methane, propane, butane, octane. These are things that you've heard of, from gasoline to lighters to natural gas. These are all hydrocarbons, and they're completely nonpolar. So I have a very short one here. It only has 2 carbons and 4 hydrogens. I can have much longer ones. Carbon is really, really good at making long chains and even like branching off those chains. So if I'm trying to draw out a molecule that has lots and lots of carbons on it, it can be both tedious to draw and hard to look at. So if I were to write everything out, on the left-hand side here, you can see there are 1, 2, 3, 4, 5, 6, 7, 8 carbons and lots of hydrogens. And that's a lot to look at. And this is actually kind of a short molecule. Sometimes they can have 18 or 19. Sometimes they form rings. So instead of drawing out all of those C's and H's, organic chemists tend to do what's called a line structure. So we just use a line to represent the bond between two carbons. So this line is connecting a carbon at the very end and at the first corner. Okay. So what you need to remember is that when you see these lines, these zigzag lines, or sometimes they'll be hexagons or pentagons, every corner is a carbon, and every end that doesn't have another element is a carbon. Okay, so I'm going to count one end, then the corners 2, 3, 4, 5, 6, 7, and then the last end 8 carbons. Okay, and then everywhere that carbon wants to bond, that it's not bonded to something else, is a hydrogen. Okay. Now, for chemists, it's important to figure out what all of those are. For us right now, all we need to know is that all that is there is carbon and hydrogen. That there's anything other than carbon and hydrogen, I would have to put the element there. So is this going to be polar or non-polar? How many people think polar? Raise your hand, those of you that are here. How many think non-polar? All right, how many of you are too chicken to answer? Well, at least you're honest. Okay, so it is non-polar, right, because there's only carbon and hydrogen. Okay, but, oh, and I just did that one, so I'm going to skip it. If I have oxygen, that's going to create some polarity. Now, if I have a small molecule, it's just going to make the whole molecule polar. So I got 2 oxygens here on one side. And remember, water is also very polar. It's got oxygen in it. So this small molecule is called acetic acid. And since there's only 2 carbons, I've drawn them out. And since we're running short on time, I'm going to skip the next question as well. The next question is just, is this a polar molecule? But since we're discussing it on the polar page, yes, in fact, this is a polar molecule. Okay, because it's got oxygen in it. All right. So here's another example of a molecule that I've drawn both with all of the atoms and with the line structure. So you can see I've got one end with nothing on it, 2 corners. Okay, so that's 3 carbons. And then I've got another end, but this one has an oxygen on it. So there's no carbon at the end of this because there's an oxygen there instead. Okay, so this has 3 carbons. This is called propanol. And because it has oxygen at the end, it's a polar molecule. But once I start making that chain really, really long, then I got that oxygen so far away from all of the carbons and hydrogens that they don't really notice it's there. So propanol and the next one, butanol, are kind of our breaking point for whether or not the whole molecule is polar or just one part of it. Once we get more than 4 carbons, then the other carbons are just so far away, they don't really feel the pull of the oxygen. So this molecule has, goodness, 19, 20, 21, 22, has 22 carbons in it. So the one that's labeled 1 has 2 oxygens attached to it. That region is very polar, just like with the acetic acid. The other region, the long chain part, is non-polar, okay? So the long chain is a non-polar region. The oxygens or the nitrogens are polar. We call these molecules emulsifiers, and they're very, very important in food, okay? An emulsifier will allow The nonpolar end, we sometimes call this a tail, the fatty tail, will mix with oils. So that end might mix with my butter, or it might mix with my olive oil. The other end that has the oxygen on it is polar. It's going to mix in with the water. So when I'm trying to make a food that has both butter and sugar, both a nonpolar and a polar, I can get them to mix well by adding an emulsifier. Okay? And I think that's the end of this presentation. Yeah, it's not letting me go forward. All right, so questions. Okay, so for those people in class, Friday, you get to try this Zoom thing, see how well it works for you. On Monday, we'll discuss what it was like for you. Those of you at home, we're going to discuss for a couple of minutes tomorrow what being on Zoom was like and how you handled that. Plan to do your homework by tomorrow night and plan to do your quiz next week. And your homework will give you good examples of the chapter 1 questions that are going to be on the quiz. All right. And did you have a question? Okay, that's fine. All right. So those of you at home, feel free to log off, and I will see you all tomorrow. If you have a question for me at home, you can hang on, and I will catch you in just a minute.